Hello interwebs, welcome to Let's Fix Computers. In the last episode of the UEFI crash course, we looked at how to physically connect a programmer to the BIOS chip, or put the chip into the programmer and then dump and reprogram the contents of the chip. Now we've got those basics of how to interact with the hardware out of the way, we're going to start looking a bit closer at the chips themselves and the BIOS images themselves. So to facilitate this, I've got this Asus B450 motherboard here, so we're going to flash the BIOS on this one. Now, in the last video, I demonstrated using the SPI header to talk to the BIOS chip, but I didn't explain how to actually make up that cable. So I'm going to repin the one that I've got over there. I'm going to repin that for this motherboard and show you how that's done. And at the same time, we're also going to have a look at the BIOS chip and look at the pins on the BIOS chip and explain what they do and how it works, because this helps us understand the hardware better. And secondly, this being an Asus motherboard, the BIOS is going to be in a capsule file format. Now, high-end programmers will take this in their stride, but the more basic ones will simply say, this file is too big, chief, it won't fit on the chip, and you'll be stuck. So I'll show you how to extract the BIOS image out of the capsule file, which is a nice, easy intro into opening up the images and looking at the contents and how they're structured. So let's roll the intro and get into it. Now, I'm going to take a bit of time here to talk about the BIOS chip itself. Now, we don't need to know how it works or what each pin does, but learning this stuff helps to demystify the electronics side of this, and it makes the whole setup more comprehensible. SPI ROM chips, as a modern successor to EEPROMs, are incredibly simple data storage devices, and if we understand how the simple stuff works, you get a step closer to understanding complicated stuff. So I think this sort of thing is worth knowing, but if you want to skip along, then the chapters are down below, so feel free to. So, the chip that we have on this motherboard is a Giga device. That's what this G logo here is about, and if I just tilt this up and refocus so we can see the number on it. So we can see that it's a 25LB128D SIG to be precise. And as we learned in the last video, that means it's a 25 series SPI ROM and it's 128 megabit or 16 megabyte chip. So this one is the SOP8, SOP8 package, so it's got legs. Whereas in the previous video, we were looking at WSON chips, which are flat packages. So let's pull up the datasheet for this chip. So this is a 1.8 volt chip, and it's a dual and quad serial flash. Let's scroll down to the pinout. Now, when you're looking at the pinouts on these chips, you'll find that they're all basically identical, but they're often labeled differently. This is because of the dual and quad mode stuff, which I'm going to explain in a moment. So on pin 1 here, we've got chip select. And when this isn't enabled, think of it as being muted and deafened in a voice call. You're still in the call, and you're connected to the bus, but you don't hear anything and no one can hear you. Whereas when chip select is enabled, you undeafen and unmute, and now you're listening and can speak in the call. So this pin means that you can have multiple devices on the same data lines and decide which one you're talking to at any given time by chip selecting the chip that you want. Then chips 2 and 3 are data pins. We'll come back to these in a moment. Pin 4 is the ground. That's what VSS means. Pin 5 is another data pin. Then pin 6 is serial clock. Pin 7 is data again. And then pin 8 is power, which is what VCC means. So these pins are labeled for a chip that's going to be running in quad SPI mode. And before I explain what that means, we should look at single channel mode. So I'm going to switch to an equivalent chip made by Wimbond that's got some different labeling on it. So if you look at this diagram here, we've got exactly the same pinout, but the pins have been labeled differently. So those data pins are still IO 0, 1, 2, and 3, but we've got single channel mode labels now as well. So let's go over those. So pin 2 is now called data out, and then we've got pin 5 is data in. Those two are fairly self-explanatory. Pin 3 is now write protect, and then pin 7 is hold or reset mode. So write protect is there to make sure that we can only write to the chip when we very deliberately want to. It also means that we could have multiple chips on the same bus, even chips that are all enabled at the same time, but still only write to one of them at a time. This is going to depend on how your whole system architecture works, though. Now, a lot of chips will have a reset pin on them in order to put them into a known state. When the chip first powers up, it might settle down into some random state with garbage in its registers. So reset will clear the internal registers and put it into a very known mode, so you can start giving instructions to it without having to guess what state the chip is currently in. So now, for a proper explanation on how SPI works, I highly recommend checking out a video by Ben Eater, which I'm going to link in the description down below. Ben Eater is one of the best computer science educators I have ever seen, and I highly recommend binge watching his entire channel. However, in brief, here's what's happening. So chips like this have registers, which are small containers of data which have an address. So if you send the address of a register to the chip, let's say 01001, if we put that into the data pin, the data out pin will respond with the contents of that register. And that might be a state update from the chip, or if we feed it a register and an address, that it will then start spitting out some data that is stored somewhere on the chip. So some of those registers might be commands and modes that we can put the chip into, such as, we can tell the chip to write protect itself, or we could tell it to go into power saving mode and things like that. To send these commands, so let's say we want to send 01001, which is a completely arbitrary sequence of numbers, what we need to do is toggle the data in and clock chips. So let's say we want to send a 0. We pull data in low, so we connect it to ground, and then we pulse the serial clock pin on and then off. That sends a 0. Then we pull the data in high, so it's now at, say, 1.8 volts, and we pulse the clock again. We've now sent a 1. Then we pull it low, and we pulse the clock 2 more times to send another 2 zeros. Then we pull data in high, pulse the clock again, and then we've sent the final 1 of our sequence. So now we've sent our command to the chip. What we need to do now is keep pulsing the clock pin. And as we keep pulsing it, the chip will start responding 1 bit of data at a time, and it will start spitting out some response to us. And the system that you're designing needs to know how long that response is going to be, so it knows how many times to pulse the clock to get the expected answer. And the interesting thing about SPI is that the clock doesn't need to be synchronous. Within reason, you can pulse the clock at whatever timing you like. It doesn't have to be a fixed frequency. You can pulse it a couple of times to get some data, write that down, then pulse it a couple more times to get the next bit of data and write that down, and so on. The chip is only actually doing something on the rising edge of that clock pulse. And what this means is that if we probe the clock pin, we're not going to see a constant frequency on it. The clock only runs when data is actually being sent or received from the chip. So if you're trying to troubleshoot one of these and you probe the clock pin, you're not going to see a fixed frequency there. You're only going to see activity when the chip actually does something. So this is all well and good, but it's going to be pretty slow to receive the data out of the chip 1 bit at a time. You can only drive the clock so fast, and when the computer turns on, we need to read out the entire contents of this chip before the computer can do anything else. So that brings us to dual channel SPI mode. So if we send a command into the chip using data in to put it into dual mode, the data in and data out pins switch to IO0 and IO1. Now when we send a command on IO0 like we normally would, the chip will start responding with data out from IO0 and IO1 at the same time. And the way it does this is that the even bits will come out of IO0 and the odd bits will come out of IO1, like so. this comes through like so, and now the chip has sent to us 8 bits of data in 4 clock cycles instead of 8. So it's doubled the throughput. So now what if we did that again? If we put the chip into quad mode, now we have IO 0, 1, 2, and 3. And so now we can send 4 bits of data per clock cycle, and we've quadrupled the throughput of the chip. And so using this method, these chips can reach like 64 megabytes per second. So on power on, the readout from a 32 megabyte chip is actually going to take like half a second. So that's what dual and quad channel SPI actually means. Making a system that actually sends and receives data in quad mode is going to be a lot more complex, but the principle of operation is way easier than you'd imagine. My understanding is that most programmers are going to be running in either single or dual channel mode. You can probably configure them to run in dual or quad channel mode, but it's just not really necessary to. However, it means that under certain conditions, not all of these pins are strictly necessary. But I wouldn't take guesses as to which you really need unless you really know what you're doing and exactly what mode your programmer is trying to run in. So now we've been down that rabbit hole, let's repin my SPI cable for this Asus motherboard and dump the chip contents. So we're going to start by buzzing out the pins. So I'll put my multimeter into continuity mode so it beeps when the probes touch. And we're going to put my black probe onto pin 1 of the chip. So that's that guy there where the dot is. So this is the cable select if you want to track labels, but we don't have to. As long as we know what pin numbers are which, that's all that matters. So now I'm going to start moving along the pins on the SPI header. So these are going to be, this one is going to be pin 1, and we're going to go 1, 2, 3, 4, 5, and so on. And oh, hey, there we go. Pin 5, there's our guy. So pin 1 goes to pin 5. I'll write that down. So let's move over to pin 2. 1, 2, 3, 4, 5, 6, 7. So pin 2 goes to pin 7. That's pin 2. 3 goes to 2. That's pin 4 there, so 4 to 4. Right, that is 9. 6 to 9. 7. 8 goes to 8. There we go. Right, now we know that pin out, we need to rewire our header cable. So let me set up for that. So a quick note about the cables I'm using. These are 2mm pin pitch, not the usual 2.5 that you see. So they're smaller than normal. The ones I've got are pinned in pairs, which doesn't really matter because I can just account for that. So the way I'm mounting these up is I've just turned them all on their side like so. And I'm going to count the white wire there as pin 1. Then the black wire will go into pin 2. And then the purple is pin 3, the grey is pin 4, and so on. And that's going to plug into the header in a block like that. So that's how I'm numbering these wires. So that's how I know which color is going to where. And another important thing to note is on our pin out here, we're going anti-clockwise. So we're going 1, 2, 3, 4, 5, 6, 7, and 8. Which is very easy to forget because we're going from a left to right and across to a clockwise pattern. So yeah, really easy to get muddled up there. So if you make up a pin header and it's not working, double check that you are counting pins in the correct direction for each header you're working with because they're all different. All right, so pin 1 goes to pin 5. So that's going to be the green pin. Pin 2 goes to pin 7, which is orange. My wires are a little bit ragged, so I've got to watch out for tin whiskers, which is where you have a tiny strand of wire poking out and touching another pin. Pin 3 is pin 2, which is black. Right, I'll just pull that out and just check my soldering. Yeah, that's fine. Purple fought me a little bit, but I think that's okay. Doesn't need to be good, just needs to be on. All right. Now, one thing to notice, when I pinned this up for the MSI board in the first episode, I actually had one pin missing, the Write Protect pin, which was pin 3, I think it was. I could not find that on the SPI header. So it just seemed to be not connected to that header at all. So that would be either Write Protect or IO2. Now we know that now the programmer can send a Write Protect command to the chip just over the data pins. So it looks like the programmer was able to unwrite protect the chip just by sending that command instead of using the pin. Or it might have been that the programmer was running the chip in dual SPI mode, in which case it doesn't need pin 3 or 7 anyway. So that's why that might have worked. And this is why I was saying to you, you might not need all the pins. So if you're missing one of the pins and it's one of the I/O pins, chances are you might not need that. So keep that in mind. Right, let's plug this in and see if it works. Right, we're all hooked up. Let's switch over to the software. All right, XG Pro, show me what you got. Detect. Unknown device. Ooh. Let's run through our pins and see where we went wrong. So I'll go into beep mode. And so pin 1 should go to pin 1. Yep. Pin 2. Yep. Pin 3. Missing pin 3. Pin 4. Yep. Pin 5. Yep. 6. Yep. 7. And 8. Okay, so we're missing pin 3. So what's pin 3 then? Oh, there it is. Okay, I'm going to pull out a different programmer. All right, CH341A. Let's see what you've got. That goes that way around. Got you in the 1.8 volt position. This is my CH341A. I've got this in this 3D printed box. This was done for me by Awesome 3D Prints quite a while back. It's got this natty little storage area where I can store extra adapters. And it's got the cheat sheet on it for the voltage level selector and the chip orientation, which is cool. IC not responding. Okay, is the power on? IC not responding. Huh. One more time. Gonna check my pin out. Maybe this is just a board where it just doesn't work. What? Is it? Is it? Four? Yeah. 5? Is this? Nope, those are all connected. Okay, well that was depressing. Right, just for confirmation, I'm just going to try the pogo pin adapter just to see if I can get a read on this chip and get something out of it. There we go. That gives me a read. And read. Oh yeah, okay, I know the pins aren't working properly on this thing. There we go. Okay, well, what we just learned is that the SPI method looks like that is not the magic bullet that it initially looked like it was. There's going to be some kind of reason for this that I don't fully understand. We had continuity to all the pins, and the programmer is compatible with the chip, but for some reason or other it just didn't work, and I'm not sure why. However, we can at least continue because the Pogo pin adapter works. So we've dumped our BIOS. Let's go ahead and save that. So we've saved our dump file. And now I'll go ahead and download the latest BIOS. Alright, so we've got a beta version for the latest version of this BIOS, but that's fine to be honest. Improved system compatibility, sure thing. Alright, so let's download that. Okay, right. Now we've downloaded this, if we take a close look at the file we've downloaded, it's a cap file, that's Capsule. And it's slightly too big by 2 kilobytes. So this isn't going to fit on the chip. The file has to be exactly 16.384 megabytes. So let's take a closer look at this. Now the best thing for looking at BIOS images is this tool called UEFI tool. Now there's a million different versions of this one. However, I use a fork of the project by Wild Floor Lamp, which I will link in the description down below. So this is UEFI tool Alpha 6.0.1. And this specific version of UEFI tool has a couple of tricks that are often used in BIOS repairs. The most specific thing that it has is the ability to replace sections of the BIOS as is, which is a very dumb replace this block with this block kind of repair, which is a little bit dodgy, but you can do it when you know what you're doing. However, theoretically, pretty much any version of UEFI tool should work for what we're doing in this one, but like I said, I recommend Alpha 6.0.1. So I'm going to open an image file, and we're going to select our cap file that we downloaded. So let's click Open. And so what this does is it shows us the actual contents of this BIOS image. If I expand this out, it shows us the different regions of this BIOS. Now, this isn't a great example for getting you into BIOS regions because a lot of this isn't particularly human readable, and there are other BIOSes that have a much stronger example of showing you regions. Particularly Intel BIOSes are easier to look at from a learner perspective. However, the bit that we care about is this top section here. You can see it says AMI Aptio Capsule. So if we go down one section, we have UEFI image. So this is our actual BIOS image. Everything inside this is the BIOS. So we want just this bit. We don't want the capsule. We want the contents of the capsule. So what I'm going to do is I'm going to right click on UEFI image and extract as is. And I'll spit that out as asus new.bin. Save. And if I go into my Explorer, you can see that asus new.bin is 16.384, exactly the same size as our dump file. So now we've extracted the actual BIOS image out of this capsule, and we've got something that is ready to be programmed directly. Now, in reality, because I'm using an XG Pro here, the XG Pro software is smart enough to look at that capsule and just automatically take the BIOS image out. However, if I was using something like Neo Programmer for a CH341A, that won't do that. It will just say that the file size is wrong. So even though I didn't need to do that, it's a good example to show you this. And now already we've started opening the BIOS image up and looking at the contents and just seeing how you can start browsing this and looking what's inside of it. Now, none of this will mean much to you right now, but in future videos we're going to dig into this a little bit further, and I'll show you what stuff might look like inside it. A lot of it is all a bit mysterious. You're not going to understand all of this I don't understand all of this, but at least I can show you how to start approaching that. So now we've extracted our UEFI image from the capsule, let's program that onto the chip. So I'll open our extracted file. So let's go open, and I'll select asus new.bin. Okay, so now we've got that loaded up into the buffer here. And now I'm going to program that onto the chip. And I'm going to wish I'd desoldered the chip, because now I've got to hold this wretched thing in place while we program it. So I'm going to get nice and comfortable here. And we're going to go program. Now I have to hold very still for about 2 minutes. See you after the cut. There we go. Right, and that chip has now been programmed with the latest BIOS. So that's all I've got for you in this video. So if anyone knows why my SPI header cable here didn't work, because there's probably some experts who are watching this somewhat skeptically, but yeah, if anyone knows what went wrong here, let me know in the comments, because I don't know what went wrong here and I'm curious about that. If nothing else, it does show that there are some unknowns, and also I think what we're learning here is just there is no magic bullet for talking to these chips. There's going to be some things that work. This cable worked like a charm on the other motherboard, and the pogo pin adapter, that is fine in a lot of instances, but no good if you've got a slow programmer. Desoldering the chip, that will work most of the time. You can tell that I've desoldered this one before when I've been messing around with the board, but that might not be viable if you're not familiar with soldering. So perhaps looking at all of these and being prepared to use whatever method is appropriate for your current situation, that's the true skill. Anyway, I hope you guys found that interesting. Thanks for watching, and I'll see you in the next one. Bye for now.